Today we're going to be talking about is fluid dynamics. So first off, we got to talk about, before we talk about fluid dynamics, is what is a fluid? Okay, a fluid is any material that flows. That kind of makes sense, and takes up the shape of a container. But here's the interesting thing. A fluid can flow because the particles easily move past each other. Things that include are fluids that include are liquids and gases. This is the part that most people don't realize, is that gases are considered a fluid. Most people think only liquids are. Solids cannot flow, thus are not a fluid. So when we talk about fluids, we're talking about liquids and gases. So you can see here a water going over is flowing. We have air flowing over a car, and here you can see how the car has some of these the flow of the car over, and you get some turbulence over here. Compare that to a big block where you have a lot of turbulence and a lot of weirdness going on. We'll talk about pneumatics and hydraulics here in a moment. So let's talk about density. Density is symbolized by the letter rho, which is actually, it looks kind of like a P. It's not P, it kind of has a curly Q P-ish look to it. But it is that is the actual unit for density, not D. We just use D when you're in middle school because it was a lot easier than teaching you the Greek alphabet. And it is just mass divided by volume. The metric units is always kilograms per meters cubed. It's sometimes converted into grams per centimeter cubed or grams per milliliter. You can have various different variations. That's just multiplying it by 1,000 or dividing by 1,000 appropriately. Now, water at 4 degrees Celsius has a density of 1 gram per cubic centimeter or 1,000 kilograms per cubic meter. Now, specific gravity of a substance is a ratio to its density, and since density of water is 1 in grams per cubic centimeter, then if you use grams per cubic centimeter, the specific gravity is the same number. But if you change it into, let's say, kilograms per meter squared or standard, then the specific gravity will be a different number than its density because it's a ratio between water and that object, the density of that object. So pressure is defined as the force per unit area. It is measured in units called pascals, which is in newtons per square meter. It also can be used pounds per square inch. Now, in any water, pressure will be the same in all directions. This is called Pascal's law. It doesn't matter which direction. The fluid will always go in there. So here are some units for pressure in there and their conversions. If you want to write these down, this would be a good thing to have so that you can easily change it from one unit to another quickly. So pascals, there's kilopascals, which is just 1,000 pascals. There's PSI, pounds per square inch. So there's 6,894.7 pascals per PSI. And then atmospheres is this number, which is 14 psi for 1 atmosphere, or 1,132 pascals. And that is 1 atmosphere. That's the atmospheric pressure at sea level. So let's look at who has more pressure. A large African elephant can weigh 7 tons, supported on 4 feet, with a diameter of about 1.4 feet. The footprint is about 250 square inches. A figure skater, on the other hand, has a weight of 120 pounds, supported on 2 skates, each with an area of about 2 square inches. So which one has more pressure? Well, it is force divided by the area. So the African elephant weighs about 7 tons, which is about 14,000 pounds, and its area is 250 square inches, but it has 4 feet, so we have to divide that by 4. So that becomes a pressure of 14 psi. On the other hand, the figure skater is 120 pounds, significantly less than an African elephant, has 2 feet and 2 inches, but it has a pressure of 30 psi on those skates. In other words, if you were to get stepped on by an African elephant or the figure skater, you would actually want the elephant to step on you. It would actually cause less damage, at least in this case, because the figure skater would just cut you. All right. Now, pressure in a fluid. Pressure is defined as force over area, and it is also the rho GH. If we take out what is the pressure equation, we can plug it in, and it is just rho times area times H times G, and then we cancel out our A's, and it comes out as this equation. Write that down. Pressure is rho GH. The density times gravity times height. So if we know how high or how the depth of the water is, we know what the pressure is. So calculate how much pressure due to the liquid would be on a 92 kilogram person if they were 99 feet in salt water. The density of salt water is 1030 kilograms per meter square. Express your answer in both kilopascals and atmospheres. All right, so again, it's rho GH, rho being the 1030, times the 9.8, that's gravity, it's 9.8, and times that by 99 meters, that gives us a depth, a pressure of 999,306 pascals. We divide that by 1,000, and that gives us 999. We'll round to 1,000. It's basically 1,000 pascals worth of pressure. If we were to divide that by our atmospheric pressure of 325 pascals, it gives us 9.86 atmospheres. Now, pressure of a fluid. A swimming pool that is 8 feet deep measures 40 by 60 feet. A drain valve at the bottom of that pool is 10 inches squared. In that area, what is the pressure at the bottom of the pool, and what is the force on that valve? Okay, so we want the pressure. So pressure is rho GH, and wants the force. So we're going to look at both equations. So pressure is going to be the density of the pool. So rho GH, and it's going to be the which gives us this 15,979.52 pounds per square inch. Now, everybody's like, where did this 32? That's gravity in the standard units, okay? And what about the 62? That is the density of water in, this is the density of water in standard units. Okay, so then that comes out as, if you change that into its PSI, that comes 110 PSI. Then we can figure out the force acting on it. Well, the pressure is this number, 110, or basically rounded to 111, and we know it has an area of 10 square inches, so then we can convert, and the force becomes 111 times 10, which gives us 1,109.6 pounds of force being put on that little drain there, and that the valve has to stop 1,000 pounds worth of force anytime this pool is filled up to 8 feet deep. Now, atmospheric pressure and gauge pressure. Atmospheric pressure is going to be always 101,300 pascals. We call this an atmosphere pressure. It also equals 14.7 psi, or these other values. Other values of pressures is inches of mercury, millimeters of mercury, torr, bar, psi. We're just going to deal with this. It is basically, if you think of it, pressure is just how much air is sitting over your top in a square inch. And if you were to put a 14.7 pound bar that is 1 square inch and put it on your thumb, that is the pressure the atmosphere pushes down on you. Now, the reason you don't feel that crushing force is because the cells in your body maintain an outward pressure that balance it out, and so you don't feel that crushing effect. Now, gauge pressure, though, gauge pressure takes into account that there is atmospheric pressure. And so when the gauge reads, let's say this one right here at 1,000 psi, that is not adding in the atmospheric pressure. So that's 1,000 pounds per pressure, but you have to add in the atmospheric pressure. So if it reads 1,000, you have to say 1,000 plus the 14.7, and that gives you your absolute pressure. So your front wheel tire says right here that it needs to be pressurized at 33 psi, while your spare tire needs to be at 60 psi. So we're going to look at the 33 psi front tire and rear tires. What is the absolute pressure? Well, we take 33, add 14.7, and that gives us then our, that's going to give us our 47 psi. Now, Pascal's principle says that pressure applied will transfer to the whole thing. So pressure in here has to be the pressure out. But if I have a small pressure with a small area and a big area out, that can change things, and I can use a small amount of force to pick up a very big, heavy thing. So pressure 1 equals pressure 2. Force 1 over area is equal to force over area 2. So what that means is that pressure stays the same on both sides, but the force can get multiplied on the right side because the area is twice as great as the left. So if I have a small area, I can lift something bigger if it has a bigger piston. We call this a hydraulic system, where a force is applied on one piston increases the fluid pressure throughout the fluid. If the second piston has a larger surface area, the force is then multiplied and it increases. So if you add a force applied to this piston, the piston then will transmit that through the fluid to the other side. Now, if it has a larger area, again, larger area means we can do a larger force, and it can actually lift up much more weight. So we can see here a small cylinder is applied by an air compressor, can push up a really heavy car, like in the auto shop. And here's the work, the mathematical work on this, but it's the same thing. And it's conservation of energy, meaning that the work does not go away because work is force times distance, but I'm going to be pushing with a small amount of force, but a larger distance, while my lifting up only lifts up a little bit. So what I want you to do is do this practice problem. All right, so now that you have had time, a hydraulic press has an input cylinder of 1 inch diameter and an output cylinder of 6 inches in diameter, assuming 100% efficiency, and find the force exerted by the output piston when the force of 10 pounds is applied in the input. So what that means is we have our force times our area of our 1 is equal to our force times area of our 2. Now our areas are going to be pi r squared, so we have to figure that out first because it's giving us our diameters. So again, we have to take that into account, and we have to half these because these are diameters. We need radiuses. So a half squared times pi gives us these numbers. 3 squared times pi gives us this. Then we'll take our force, 10 pounds, times our area of 0.7, that gives us our, and then our is equal to our force 2 times our second area. So that gives us 360 pounds that lifted up. If the input piston is moved through 4 inches, how far will it go? Well, we can go with the distance here. Force times distance of 2 is equal to force distance times distance 1. This is the conservation of energy. Work is equal to work with 100% efficiency. So we know what our forces are. We know that the distance of 1 is 4 inches. So we do 10 over 360.1 times 4, and it goes up by 0.11 inches. So by applying 10 pounds of pressure on one side, it raises 361 pounds on the other side, and it lifts, the one goes down 4 inches, but the other one goes up by only 0.11 inches. Fluid is in motion. So fluid actually moves, and so the flow rate and that equation is called the equation of continuity, meaning that the flow rate as it passes from one area to another is always going to be the same. It's continuous, and the equation is the density of the fluid times the area of the fluid that's traveling through the cross-sectional fluid. So you can think of a pipe's area times the velocity of that fluid is equal to the density of the fluid times the area of the fluid times the velocity of that fluid afterwards. So what that means is as I'm going through a pipe, if the fluid doesn't change density, which it usually doesn't, then as it's flowing through, then we can just get rid of the densities on both sides, and it just becomes the area times the velocity is equal to the area times velocity. What happens if this number goes down? Well, then this number has to, where the pipe widens, the flow is slower, but as it gets narrower, that velocity will increase. Because as the area goes down, this number has to go up to counteract it. So if this area goes down, let's say half, in order to keep this side equal, this has to go up by twice, and your speed of your water goes up. Now, Bernoulli's equation is a really complex looking equation, but it is not that hard. Okay, it's actually just the conservation of energy put into pressure terms. So what we do is we say that the pressure 2 is equal to this portion, which is going to be the second, which is the kinetic energy equivalent of water. So it's 1/2, instead of mv squared, it's just 1/2 rho v squared. So it's just taking the pressure version of the kinetic energy, and that's going to be to your potential energy, which is the rho g height, or h, or the y, and how much is it lifting up. And that has to be conserved, meaning on this side has to be the same as this side. All these numbers have to equal this side. You can't lose energy. So Bernoulli says that, let's say for instance you have a pipe, and it starts at a lower and it goes to a higher. Because the pipe's diameter stays the same, the velocity does not change. So that means I can get rid of my velocities. But this means that we can also cancel out the 1/2 rho v squared term. Now, as the water goes up the hill, the pressure, as this goes up, the height, it gains height. That means that in order to do that, it has to take energy from somewhere. So as we started at a lower distance, the pressure is high. As we go up higher, the pressure decreases. So if you don't change the pressure will go down. So let's actually look at a problem. A pipe brings water from a source that is 5 meters to a hill that is 10 meters. What is the pressure change? What is the pressure change? So again, we can do that same equation, Bernoulli's equation. Again, we can cancel out because the pipe stays the same. And so we plug in our numbers that we know. Pressure. Well, it starts off with 2 atmospheres of pressure, because it says there in our picture. And so we're going to change that into pascals to make our lives easier. And we want the pressure at the second half. We don't know what that is. Density of water is 1,000. Gravity is 9.8. Height starts at 5 and it ends at 10. So we plug in all our numbers that we know. Pressure is pressure 2, which is over here. We don't know what that is. Plus our 1,000. So that's going to be our 1,000, our density of water, times the 9.8 gravity, times our height, the 10, equals our pressure 1, 2 atmospheres, times our pressure of 1,000 times 9.8 times 5. We plug it into the calculator, solve for it, move everything around, and that comes out as 1.52 atmospheres. That means you dropped it by a factor of 1/2 an atmosphere's worth of pressure. Now, what about a narrowing of a pipe? Well, you can do the same thing using Bernoulli's principle. We find that the speed of pressure water coming out of a pipe is different. So we can calculate the velocity of a pressure of water coming from a 5 centimeter pipe to a larger diameter pipe, a 10, and the incoming pressure of 2 atmospheres. Same exact thing, but this time we have to use our velocity, our continuation of flow equation, where the area times velocity is equal to area times velocity. So we have to include that as well. But because we're not changing any heights, we can get rid of those quantities. So first we have to figure out what is the velocity based off of our distance, our diameters. So what we're going to do is we're going to take this equation, solve for the velocity at the end, so we can figure out what our velocity is at the end of the pipe. So we're going to take it. We know our distances, our diameters. Again, we have to half those numbers to get us our radiuses. So pi r squared over 5 pi times it by 4. Our pi's actually cancel out. That's nice and convenient. And so it just becomes 2.5 squared times 4, which is the velocity initial of the water, over 5 squared, and that gives us our velocity, which gives us 1 meter per second. So that water comes in at 4, leaves at 1. Now we can plug everything in. I've already rearranged it for us. So the pressure 2 over here is going to be the 1/2 rho v squared. We know what the velocity is. It's 1. So we go 1/2 times the so we have our pressure, 2 times our atmospheric pressure, so we get us our from atmosphere into pascals, times plus 1/2 1,000 times 4 squared. That's our velocity initially, and then minus that from our second set of circumstances, which is the latter half, 1/2 rho v squared, which is our speed, the end, and that comes out, and I do some simple algebra. I'm going to do some factoring. You could put this into a calculator. It really doesn't matter. I'm just showing you kind of the algebra here. You literally put this whole thing into a calculator and it would just pump it out as 2.074 atmospheres, or in pascals, 210,150 pascals. All right, now we can do the same thing using Bernoulli's a spigot. Noticing that you have an open container and it has a spigot. How fast is the water coming out of the spigot? Well, the pressure is the same because it's atmospheric pressure here and atmospheric pressure here, and there's nothing. And the velocity here at the top of this is 0, so it's not moving, not even closely how fast this is. So we can get rid of those terms. So then we just are left with this. 1/2 rho v squared is equal to rho gh minus rho gh. So I'm going to factor out my rho's and g's, factor it out because my difference is in height, and my rho's cancel out. That was nice. So it becomes 1/2 v squared is equal to g times differences in height. My half I can move over, and that becomes v squared is equal to 2g times the change in h, and I then square root both sides, and that gives me that number. So this is just one way of doing this problem. So we can do this exact same problem, and we can then calculate this problem, where it just becomes the square root of 9.8 times the height difference, 6. That means I'm going to have a velocity of 10.8 meters per second. Now, the application of Bernoulli's principle comes into like airplanes. As air comes over the top of the surface, it will actually go faster than the bottom, and that means the faster you are, the lower pressure it is, and that's going to pull up on the wing. Underneath is high pressure because it's going slower, and that means it's going to be going it's going to be pushing up. So you get a pull on the top surface and a push underneath the surface. If somebody throws a curveball, the ball curves and spins. That's going to grab some of that air as it spins. This is going to cause an unequal amount of force on one side of the ball, and that can cause the ball to curve left or right, depending on which direction they spin it. If you have let's say a blockage, a constriction in one of your arteries, if you suddenly stand up, there's going to be that pressure change because you just went up higher in altitude, or higher in height. Then the blood all of a sudden is going to have to go through that narrow chamber very, very quickly, and that's going to cause a drop in pressure. And that drop in pressure can then lead to a blackout where a person will faint due to just standing up. This one is also called the Venturi meter. Venturi meters are really cool ways of detecting how fast fluids go based on the pressures. Because if the pressure goes up, we know that as it narrows to a specific known size, the pressure goes down. We can actually calculate how fast that fluid goes through, and we can calculate fluid flow very accurately just by knowing the exact diameters of this. And so these will put into pipes and or airplanes as they fly through the air, and just all they have to have is a pressure gauge and the known diameters of those pipes, and we can actually tell you exactly what the fluid speed is. So if it's a pipe, we can know that. If it's air, we can also know that. Here in nature, even groundhogs and prairie dogs will actually use this to help clear out any poisonous gases like carbon dioxide out of them. The wind will blow over the tunnel. The higher the tunnel is, that will suck the air out, cause a higher pressure, and this will be a lower pressure, and it will actually cause a breeze inside of the prairie dog tunnel. I know this was a longer video, so if you have any questions, please review the PowerPoint and then write down any questions.